let's get into talk about electricity, and by that we mean electrical charge that's flowing through a circuit. One of the most common analogies that's used in physics to try and make it easier to understand electrical phenomena, because it's something that you can't really see as it flows through the wires, is by using water as an analogy. Okay? So right here, I've drawn out a simple water circuit. Imagine if we had a pipe, a closed-off pipe, full of water. Now, in this pipe, there are a few things that I want to point out. The first thing I want to point out is there's a little turbine in the pipe, right? Something like a water wheel that will spin as the water flows over it. So as the water moves through the pipe, it's spinning this turbine. You can see something like this if you look up videos of a hydroelectric dam or a very simple water mill, right? A spinning object powered by the water. Now, this shows us that the water can do work. Work is being done as the water pushes and spins the turbine. We could then use that spinning motion to, in the example of a water mill, maybe grind up some wheat into a flour or powder, right? So we can see that the moving water can do work. Another thing is that there's a pump inside this closed water circuit, and that pump is forcing the water ahead of it, right? It's kind of doing the opposite of a turbine. Rather than allowing the water to move it is moving the water. You've probably seen pumps before as well. For instance, in a basement that floods, you might have something called a sump pump that pushes water up and out of the basement, right? So imagine this pump increasing the pressure ahead of it because there's lower pressure water behind it. Talking about pressure in water, this is kind of the push behind the water, right? This is what's driving the water before it. This push is being increased by the pump. So we've got high pressure here, and we've got low pressure coming in and being converted to high pressure here, right? And that push is taking place throughout the entirety of the flow in this water circuit. Another thing we look at is the flow rate of the water, right? How fast is the water moving through this pipe, right? The larger that pipe is, the less resistance there is. The smaller that pipe is, the more resistance there is. And that's going to have an effect on flow rate. So before we jump into resistance, I just want to point out again, there's a flow rate in the water. It's how much water is actually moving through this pipe. Then we get into talking about resistance, right? Resistance is when something is impeding the flow of the water. So in the case of this, I drew the water being constricted by a smaller pipe. The pipe has gone from large to small, and as it becomes small, less and less water can physically move through it. But in addition to that, there's also resistance being produced by the fact that the water is now bumping into each other, right? Water is only compressible to a certain degree, and so all of these atoms start resisting each other, bumping up against the edges of the pipe, bumping up against each other, an increase in resistance. We've got less flow, right? This resistance can obstruct the pipe. Other things that might resist might be like dirt or sand in the pipe, right? Now again, this is a simplified analogy, but we're now going to take and come over with what a battery is in a circuit and how a simple electrical circuit might work, and draw the analogies between the two of these, okay? So first thing I want to point out is we're talking about work. Water moving through a pipe can do work. Well, so can electricity moving through a pipe. Now you probably remember our work equation. We get work force over distance, right? Force, multiplied by distance. Work is equal to force times distance. And that gave us joules. Work is done by electrical circuits, but we generally talk specifically about the power of an electrical circuit. Some of you might have been a little bit surprised when we were doing our power calculations with us moving up and down the stairs. And as we moved up the stairs, we were able to calculate how much the power output of our legs were. And that was measured in watts. You've probably never heard of watts in anything but electrical systems before. And there's an important reason for that. That's because when we're talking about the joules moving through an electrical system over the amount of time that it takes that to happen, we can calculate the power of the electrical system, specifically in watts. Okay? So just like the water doing work inside of its circuit, we can have electricity doing work inside of our circuit. Generally, that work is something like moving an electric motor or lighting up a light bulb, but we'll talk about that a little bit more when we get to resistance. Now the pressure of the water, right, that force being applied that actually moves the water around, what we call that in an electrical system is voltage. Voltage is usually supplied by something like a battery, right? It's producing voltage, which is allowing electricity to flow through the circuit and then come back around at a lower voltage back into the circuit where the battery is then providing more of a voltage boost. As voltage moves around a circuit, it will drop around resistors, but I'll talk a little bit about a little more about that in just a moment. Voltage, the symbol for it is V, and we measure it in volts, the symbol of which is also V. Nice and simple. It gets a little bit more confusing with current. Current is similar to the flow rate, right? It's how much is actually moving through this section. So the current is moving around and around the circuit. We can see I wrote I here with its directional, moving around and around the circuit. You might be wondering, why the heck is the symbol for current an I? Blame the French. Intensité du courant is the term for current in French. Intensité starts with an I. It's I for current. They were some of the first ones, for instance, Volt, to work on electricity and to really push us forward into the equations that were used. So as a result, we take their symbol for current, which is an I. Now, the units for current are measured in amps. Amperes is specifically the name of it. It's named after a man named Ampere, but we usually simplify that to amps, the unit symbol which is A. Okay? Now we get into the delightfully confusing one, resistance. Resistance, much like the resistance in the water circuit, is something that's going to slow down or impede the amount of electricity that can actually flow through. Now, this is very similar to the way that the pipe gets constricted. How is resistance measured in an electrical circuit? It depends on how large the pipe or the wire is that's carrying the electrical charge. Larger wires usually have an easier time because the electrons literally don't bounce around against one another and cause resistance with themselves. Longer wires will usually have a higher resistance because as they travel, they tend to bump into the edges of the wiring into themselves. More and more resistance is produced. Smaller wires will have more resistance as well. In addition, the very makeup of the wire itself, much like if we had a very rough pipe, right, a concrete pipe, the water's going to have a harder time moving through that than a very smooth PVC pipe with very little friction on the edges. Same thing happens with, for instance, copper wiring. Copper wiring makes it easy for the electrical signal to travel. But there are other metals that are not so easy to travel that can increase the amount of resistance. Okay, the symbol for resistance is R, R for resistance, and the unit for resistance is measured in ohms, its symbol of which is a Greek omega letter. So while we're talking about circuits, very, very simple circuit like this, I want to point out two things that are true in voltage and current, okay, that are, again, very similar to the water analogy. If we bring this over, voltage drops across resistors. And what I mean by that is that if you have multiple resistors in a row, you're going to notice that less and less voltage is supplied to each. This is very similar to if you imagined some sort of water piping or waterway, right? If there was only one water wheel in it, and there was 5, there's no units here, I'm just using an imaginary number, 5 units of water, right, is pushing that water wheel. Well, if there's only one, all 5 units of water push the water wheel. But what if there were 2 water wheels? Well, there's not enough pressure behind it to move both of them 5. You've only got 5. So what happens is we see 2.5 on one and 2.5 on the other. The voltage will split if you have more than one resistor in a row. It drops across these resistors, okay? The other thing I want to point out is that current splits at junctions, again, much like the current in a waterway. If you had a river or a pipe and that was split in two, could the same current move through both? No, that doesn't make any sense. There's a finite amount of water available, right? In a very similar way, electricity will also split at junctions. If you had 5 amps in this case, and it reaches a junction, you're only going to see 2.5 on one and 2.5 on the other. Now, these are with simple circuits. As we get more information about Ohm's law and Kirchhoff and how more complicated circuits work, you'll see how the mathematics click together. But this is a very simple circuit design, okay? Coming over, I'd like to show you an example of what I mean by this voltage drops across resistors and the current splitting with junctions with a very, very simple example that's going to be similar to what you are working with on the questions for today and tomorrow, okay? This is literally one of the questions that you're going to work on, so if you pay a bit of attention to it, you'll get one answer for free right off the bat, okay? Imagine we've got these spheres. We've got these 2 spheres that are just packed with electrical charge, okay? An incredible amount of charge. They obviously want to discharge, just like with all of our static experiments. If you've got something that is incredibly positively charged, right, and you connect it to something that is neutral or negatively charged, there is a flow of charge. There's a flow of electrons. They stabilize one another, right? It's the reason why when you are moving across, we'll say like a bit of rug, and you reach out and you touch a doorknob, you see that zap, you feel that zap, what's happening? You became charged because of the way you were moving across the rug. There was friction between you and the rug, and as a result, your charge equalized, balanced out when you touched that metal doorknob, right? This is what we're going to do here with our spheres. In addition to these two highly charged spheres, we have two other spheres, one of which is mildly charged, the other which really has no charge at all, okay? If we attach the spheres together with some bit of wiring, right, just like this here, the wiring has a very resistant piece of metal in the middle, resistor. What will happen? Which one of these will have the higher voltage drop? Well, if we take a look at this one, lots and lots of charge, okay amount of charge. That's not going to have a huge drop. But lots and lots of charge, very little charge, a lot of voltage is going to move across this piece of wire. So which one's going to have the higher voltage drop? Well, it's going to be number 2. Which one will have the higher resistance? Well, we determine resistance based on the length of the wire, based on the material that the wire is made out of, the material the resistor is made out of, and based on how thick or thin it is. In this case, we're using the same wire for each, same material, same length. It also looks like the resistant chunk in the middle is the same size for each. You'll notice in some of the questions that's not the case, so think about that one a little bit more closely. But in this one, the resistance piece is the same size in each of them. So which has the higher resistance? They're equal. No, Mr. Comer, a Q does not have a tail moving forward like that. It has equal amount of resistance in both of these spheres. Well, there is an equation that we see in electrical systems like this. It's called Ohm's law. It's pretty simple. What this equation states is that the voltage across a resistor is directly proportional to the current that's flowing through that resistor. Okay? Simple way of saying that is voltage must be equal to current multiplied by the resistance. You can, by the way, substitute this and work this out in which way you like. So in a very similar way that I might say voltage is equal to current multiplied by resistance, what if I was solving for resistance? Well, in that case, I would say that voltage over current must be equal to resistance, right? Divide both sides by I, we get V over I equals R. Another way that I'll show you real quick that a lot of people prefer to do this is by writing this out in what we call a proportion pyramid, like so. We've seen this before in power, and we also saw this in force. It comes across a few times, and the way that this works is very simple. Let's say you want to know voltage. What do? You cover up voltage. Oh, resistance multiplied by current is voltage. Cool. Well, let's say I want to know resistance. Let me cover up resistance. Voltage over resistance is equal to current. What if I want resistance? Voltage over current is equal to resistance. Very simple. So in this case, we've got a higher voltage, same resistance. Well, look at these proportions. If V goes up and R stays the same, what must change about current in order to keep these proportional? Current must go up, right? So which one's going to have the higher current across this wire? It's going to be number 2. There's a simple example of how voltage flows using this equation called Ohm's law, which we're going to be running into pretty frequently. I think Dr. Samara did a very good job explaining Ohm's law and explaining these ideas like voltage and current, but I hope that seeing this with the water analogy helped to explain how we're actually going to be using some of these ideas and concepts. Okay? Now, this water analogy does fall apart relatively quickly, which is why you shouldn't get too stuck on it. It's extremely useful in understanding voltage, current, and resistance a little bit better, but electricity is a lot more complicated than water, and it doesn't quite stay true to the same forms, especially when we start dealing with more advanced and complicated circuits. One thing that's very different about this analogy, for instance, is something that you saw when we worked on our energy labs a little while ago. During those energy labs, you took a battery, right, and short-circuited it by connecting it with a very heavy piece of copper wire, and then you held this close to a compass, and hopefully you remember what happened then. That's because that here's a little compass right here. Unlike water, electricity is doing something, right, around the piping. It's producing an electrical field, a magnetic field, right, that can have influence upon other electrical systems or magnetic systems. Just like when we took that battery and we held it close to the compass, we saw the compass spinning around crazily because the battery and its wire was producing an electrical field. Water doesn't do that. That electrical field is something that we have to take into account when we're dealing with circuits and complicated electrical systems. So just want to point out again, it is a useful analogy. It falls apart pretty quickly when you deal with more advanced systems. So use it as you will now, but remember, we should really start focusing on what electricity is in its own words, right? And these are some of the important vocabulary and concepts that we need to know.